Okay, let's dive in. We're looking at this really interesting scenario today from a nature and innovation class. We've got these two kids, Kesser and Steen, and they have a choice, right? Go look for orchids or, work on their exam project.
Yeah. And what's cool right off the bat is Steen's idea. He figures, hey, why not do both? Let's take the laser pointer IR thermometer with us while we're hunting for orchids. Practice using it out in the field.
Which is a great idea. That mix of tech and nature often sparks something interesting, doesn't it?
It really does. And it's not just any day. There's this backdrop
Yeah.
of a serious drought, like 2 months with hardly any rain.
Mm-hmm. You hear about farmers watering, worries about fire risk. You can almost feel how dry it is. And Kessler, he's thinking bigger picture, too. How's this affecting the local wildlife? Frogs, toads, snakes.
Yeah, and even connects it to global cooling thoughts. They're young, but they're definitely observing their environment closely.
Absolutely. It shows they're already thinking about, connections, how local stuff relates to bigger patterns.
That kind of curiosity is, well, it's everything in science, isn't it?
So what do they do first? The logical thing, you'd think. They get a big pot, fill it with water, try out the thermometer. Steen's calling out numbers, Kessler's writing them down. Seems like a plan.
It does, on the surface, trying to get a baseline. But, this is where the puzzle really starts. The readings Steen's getting, they're all over the place. Kessler calls it hopping and dancing like a carnival in Rio.
That's such a great description, and it's their first real sign that maybe this tool isn't quite as simple as pointing and shooting.
Exactly. Expectations meet reality, right?
So they do the smart thing. They go talk to Professor Hendricks.
An expert, yeah. And his advice, it's classic, really.
Go back and read the manual. Sounds simple, but how often do we actually do that?
We really should more often. Because the manual holds the key, doesn't it? It spells out how the designers intended it to be used.
And what does it say? The crucial bit.
It says, this thermometer is calibrated for measurement on a matte black surface.
A matte black surface. And you can just picture Steen's reaction like, seriously, who makes a smart thermometer you can only use on a pizza stone?
It's funny, but it highlights such a common thing, right? We assume tech works a certain way.
Without actually checking the fine print.
Precisely. And Kessler immediately thinks about all the times they've seen people pointing these things at, like hot asphalt in the sun or walls in the shade.
Yeah. And he starts wondering, were any of those measurements actually reliable? It's a big question about data quality, really.
It is. If you don't understand the tool, how good is the data you collect? Professor Hendricks explains that the thermometer reads the infrared radiation, the heat coming off a surface. Matte black surfaces are ideal. They radiate heat consistently. But liquids, especially water, that's a different story.
Okay, so let's get into that. Why were the water readings so jumpy? The carnival in Rio?
Well, the main problem is reflectivity. Water's shiny surface doesn't just emit heat nicely towards a thermometer. A lot of that infrared energy actually bounces off.
Ah, like sunlight glinting off a lake. Same idea, but with heat radiation.
Exactly like that. Plus, the water in the pot probably wasn't all the same temperature. You might have slightly warmer spots, cooler spots. So even tiny movements when Steen was pointing the thermometer could mean he was hitting different temperature zones.
So the reflection and the uneven temperature, that explains the wild readings.
Yeah. So that first test, even though it didn't give them a stable number, it taught them something crucial about the thermometer's limitations.
Okay, so water's tricky, but what about Steen's original plan using it out in the landscape, on their orchid hunt?
Right. This is where the real learning happens outdoors. Professor Hendricks tells them it will work much better on things like soil, rocks, tree bark, leaves.
Because they're more solid, less reflective, more matte.
Generally, yes. They tend to emit heat more like that ideal matte surface. But there's a big but.
There's always a but, isn't there?
Huh? Usually. In this case, it's direct sunlight. If the sun is beating down on a surface, the thermometer might pick up the reflected sunlight's heat, not just the surface's own temperature.
Okay, so pointing it at a rock that's been baking in the midday sun might give you an artificially high reading.
It definitely could. You have to be mindful of that reflection.
Now, these thermometers often show temperatures with decimal places, right? Kesser and Steen wondered about that too. Does that extra precision actually matter when you're outside?
That's such a good question. And Professor Hendricks gives a really practical answer. He says basically no. Outdoors, you've got so much variability. The surface itself, the angle of the sun, a bit of wind, maybe some moisture evaporating, all these things introduce uncertainty that's usually way bigger than those fractions of a degree. So those decimal places give what he calls a false sense of precision.
Right. It looks precise, but it doesn't really reflect the reality of the complex outdoor environment.
Exactly. It's not adding truly meaningful information in that context.
So it might make you wonder, is this thing actually useful outdoors at all if it's not super precise and sunlight messes with it?
And that's fair.
Yeah.
But Professor Hendricks points out its real value isn't necessarily getting a single hyper-accurate number. It's brilliant for comparison, for seeing patterns.
Ah, okay, like comparing the temperature of different things.
Yes. Compare the grass in the sun versus the soil in the shade. Compare a rock to the bark of a tree nearby. Compare the water in a puddle to the dry path next to it. The differences you measure, those are often significant and tell you a lot about the microclimate. Those big jumps in temperature are real.
Can you give some examples? Like what might Kesser and Steen actually find out there?
Sure. Imagine they pointed at the asphalt bike path. Maybe it's really hot. Then they pointed at some bare earth, then a patch of grass, then deep into the shade under a big tree. Professor Hendricks suggests they could easily see differences of, say, 10 degrees Celsius, maybe even more, between that hot path and the cool, shaded forest floor.
Wow, 10 degrees. That's a huge difference, just a few feet apart.
It is. And it's not an error. It's showing how different surfaces absorb sun, how shade cools things down, how evaporation from plants plays a role.
So they're directly measuring microclimates.
That's exactly it. And this experience helps them understand bigger ideas, too.
Like what?
Well, like the cooling effect of forests. By seeing how much cooler it is under the trees, they get a hands-on feel for how vegetation moderates temperature. Forests provide shade. They release water vapor through transpiration, which cools the air. The soil holds moisture. It connects their little thermometer reading to why forests are important for regulating climate, capturing CO2, the water cycle.
It connects the dots from their handheld device to these big global processes.
It's a simplified model, as the professor notes, but it's grounded in their own observations. That's powerful learning.
Okay, let's circle back quickly to the water problem they started with. Professor Hendricks made a key point about what the thermometer actually measures in the water, right?
Yes, absolutely crucial. He emphasized it measures the surface temperature only, just the very top layer.
Not the temperature deeper down. For that, you'd need
A regular thermometer when you stick in the water.
Yeah.
An immersion thermometer.
Got it. And he mentioned other tricky things with water measurements.
He did. Steam was one.
Oh,
If there's steam rising off the water, it can get between the thermometer and the surface and mess up the reading.
so maybe measure from an angle to avoid the thickest steam?
That's the suggestion, yeah. Also, reflections. Not just infrared bouncing off the water itself, but reflections of other hot things nearby onto the water surface you're aiming at.
Okay. So if a hot lamp is reflecting the spot you measure, that could skew it.
Potentially, yes. He also briefly mentioned emissivity, basically, how well a surface emits heat. Water's pretty consistent, so the standard setting on the thermometer is usually fine, but it's another factor in the physics of it all.
So for Kesser and Steen, or anyone trying this on water, remember it's just the surface temp, watch out for steam, and be aware of reflections.
And hold it steady. Stay within the right distance like the manual says. It's about using the tool smartly, knowing its limits.
It really seems like Kesser and Steen learned a ton, starting from that wobbly reading in the pot of water.
They absolutely did. Their journey from confusion to understanding, guided by Professor Hendricks, it really highlights something important about science, doesn't it?
What's that?
That having a cool tool isn't enough. You have to understand how it works, why it works, and importantly, when it doesn't work, or at least when you need to be careful interpreting the results.
Yeah, understanding the tool is as important as the data itself. Professor Hendricks really helped them bridge that gap.
Definitely. From the specifics of matte black calibration to the broad cooling effect of forests.
So here's something for you, our listener, to think about, sparked by Kesser and Steen's adventure. Just take a moment sometime today or tomorrow. Notice the temperatures around you, but think about the surfaces. Feel the difference between sun-baked pavement and shaded grass. Touch a metal bench versus a wooden one. Why are they different? How do sun, shade, and the material itself create these tiny little climates all around us? It's kind of fascinating when you start paying attention, just like Kesser and Steen did with their thermometer. Well, that brings us to the end of this deep dive into Kesser and Steen's temperature quest and the world of IR thermometers. Thanks for joining us.
Yeah, we hope it's giving you some food for thought and maybe encourages you to look at your own surroundings a little differently, a bit more inquisitively.
And don't forget to subscribe to the deep dive for more explorations into the science shaping our understanding of the world. Okay, let's dive in. We're looking at this really interesting scenario today from a nature and innovation class.